sometimes you'll see the terms one-tailed test and two-tailed test. Just quickly, and it affects the t-value that you are using again. Sometimes you're interested in the total population. Do they, and it doesn't matter if it's bigger or smaller, do they differ? We use the two-tailed test. If I'm only interested in one direction of difference, in other words, is it bigger or is it smaller? One direction. I use a different t-value, and that t-value there would, in the table you saw 0.05, that t-value there would then be 0.025. In other words, because I'm only working with the half of it. Okay, and you can see it's a slightly smaller value. Okay, does that make sense? Okay, not. Don't worry about it. Okay, you'll see these terms now and again. Most of the time we're only interested in.
So on the two-tailed test, you're actually asking, is it different from, as opposed to a one-tailed test, you're saying,
is it bigger?
Larger than?
Or is it smaller than? So in other words, I'm interested in only one tail of the population and not in the whole population. Okay, right. So, and I put that in there because you'll see that in the literature. Or you'll see a stats table and it'll say one-tailed test or two-tailed test, just so that you understand or have an idea of what it means. Okay. Don't get hung up about it. Generally, when we do field trials, we're interested in, is there a difference? That's it. Okay. And the two-tailed test is more than adequate. Okay. So when you get into more specialized things that it might become important. Okay. Right, it is nearly 5 o'clock, but maybe I'm going to take another 5 minutes. It might take longer actually. Let me do the chi-square test. Right, now another, and this becomes more important to breeders and people involved in testing hypotheses. The chi-square test, generally, when we do a chi-square test, the form of your data is important. So I just want to start that when you do a chi-square test, you're normally working in counts. You don't use percentages or ratios. You actually use the real numbers. And it's generally related to counts and not continuous data. Okay. The chi-square requires that you use the numerical values. And the chi-squared is a statistical test commonly used to compare observed data with data that we would expect to obtain according to a specific hypothesis. So what we can do is we can take something very simple, Mendel's law. I think you all know Mendel's law. And I'm not always convinced that he got it right, but never mind. Okay, so if I've got, let's say, a question, I expect there to be 10 of the 20 offspring that I measure from a cross should be male. That's my model, and I'm saying I observed 10 males. So I made a cross, and I expected half of them to be male, and I found that 8 were males. Now the question is, remember you've always got error, so it's not absolute. The question is, how well does that fit what I expected? Very simple question. Were the deviations between the observed and the expected the result of chance, or were they due to other factors? The chi-square null hypothesis, and as I said, I don't like null hypotheses, no significant difference between the expected and the observed. Now the very basic formula that you use for the chi-square, the chi-square value is there. It's the sum of the difference between the observed and the expected. And you'll notice I put a square in there again because I want to get rid of the negatives, divided by E, which is the expected. So in other words, it becomes essentially a ratio of the expected. Okay, and I do that for all the possible categories. Okay, so let's take a typical Mendelian type thing. I have a population of 880 plants, and I look at the segregating population, and there were 639 with green seeds, there were 241 with yellow seeds, and you're asked to propose the genotypes of the parents. And the hypothesis is that the green is dominant over the yellow. It's a very simple. So I expect, based on that, a 3-to-1 segregation pattern. Mendel's first law. Okay. So there's my possible combinations that I have, and it'll give me then because green is dominant, it will give me a 3-to-1 segregation pattern. Okay. I then put that in a table. I have my observed, yellow, green. I have my expected. Now, I have 880 plants, and I expect 3/4 of them, 3-to-1, yeah, 3/4 of them to be green, and I expect 1/4 of them to be yellow. I work out the deviation between the observed and the expected. Okay. And I get 21. The deviation is squared because I have to get rid of the negatives, and they just happen to be the same. Okay. That's purely coincidental. I then divide by the expected. So in other words, I take my 440 and I divide it by 660. And I get a value. I take my, 421, and I divide it by 2. And I get a value. And when I add those two values together, I come up with a value of 2.6 or 2.7. Now, what does that mean at this stage? Nothing. I have to go to a chi-square table that you'll find in every stats book. Okay, I had two comparisons that I was making. I lose my degree of freedom. Okay, so I have 1 degree of freedom. I want to work on the 95% probability level, yeah, or 0.05, and the value is 3.84. Right, now this figure can start making sense. Okay, that figure there is smaller than the chi-square table figure. So that I can then say that these figures fit my model of 3-to-1 segregation pattern. If that figure was bigger, then I'd say it's being affected by something else, and it doesn't fit the model. Now that is very simply the chi-square test, and the breeders will use it a lot. The next example I have is a similar sort of thing, except that we got more genes involved here, and I expect a 9-3-3-1 segregation pattern. And I find that I have 328 yellows, 90 wrinkled yellow, round green, wrinkled green. I have a total of 556. The expected based on that segregation pattern, I split that up according to that ratio. I work out the deviations. I take the square deviations divided by E, okay, and I add the whole lot up together, and I get a total of 4.1. That number means nothing until I go back to my table. I had 4 patterns that I was measuring. I lose my 1 degree of freedom. I'm now on 3, and you'll see that the chi-square that I require is 7.8. And because that calculated chi-square value that I had there was 4.10, it's smaller than 7, I can say my segregation pattern was within that model. Okay. So the chi-square is used then to work out whether the observed segregation patterns or whatever I'm measuring, okay, fits a model of sorts. Okay. Now there is a situation where you might not have a model, and you have to then work out a model from a matrix table. We can maybe have a look at that tomorrow, but in the example that I gave you, I have a little explanation there as well. If you want to then work out whether males and females in nematodes differ or juveniles differ from, you can work out a model based on the matrix, and you work on the percentage of totals. Anyway, it's in there. We can have a look at that tomorrow briefly. But the chi-square is a very nice method for checking whether what you're observing fits an expected model that you may have in mind. Right, and I think before we go into analyses of variance, let's stop at that point. Remember the questions you're asking. Do the two cultivars that I'm testing differ? T-test. Do the patterns of segregation or patterns of behavior, whatever I'm measuring, fit a certain model? We then get into, not randomized block design, we get into chi-square. Okay. So you have those two basic analyses, and they're very simple analyses, but they can tell you a lot about the behavior of a population that you are looking at it. Be it a small population of two cultivars, a larger population of segregating traits, whatever the case may be, right? You've got these two analyses. Tomorrow we'll go have a look at the analysis of variance, and those will then also increase in complexity. But from what we've already done, the analysis of variance is nothing new, because you already know what variance is. Okay, you know what t-values are. Okay, it's going to be a walk in the park. And they're going to tell you a lot about the questions that you're trying to answer. Okay, so we'll build up as we go along.